Are you on Zoom? Yeah.
Yes, I'm on Zoom. But I shared my screen.
Oh, thank you. Do you need this?
No, I don't need that. But is this?
This is just the laser pointer.
Okay, good. I'll use it.
It's like a funny looking one, but
What's the pointer?
I think the thing that looks like a laser.
Does that work? Am I on?
I think I introduced you first. Okay, so the last speaker of the day probably needs no introduction. He's one of the most energetic, high-energy physicists that I personally know. Nima Arkani-Hamed is going to tell us about dual surfacehedra for all-loop scattering, or how positive geometries of particles discover strings. Besides being a movie star who featured in the blockbuster Particle Fever, Nima, of course, also is the recipient of the Gribov Prize, is the recipient of the Fundamental Physics Prize, and made multiple contributions to particle physics, cosmology, string theory, and many, many other fields. And recently with his collaborators, he tried to teach us a new way to think about quantum field theory in terms of geometric methods. And I think this is also something in line of this research that he's going to tell us about. Thanks a lot, Nima.
All righty. All right, let's see. Is this working okay? Hold on. That's good. All right, excellent. Well, it's really a fantastic pleasure to be here. This is my first real academic trip of the quasi-post-pandemic era. So it's really an honor to be here. I first met Mani, I can't remember, maybe 10 years ago, something like that, when he visited me at Princeton, and we started talking and ended up talking for 6, 7, 8 hours all day. You all know him as of course, a wonderful person, a benefactor of this fantastic institute here. But I say this in all sincerity. I think for me, Mani's also a remarkable, sort of fascinating, deep person. And I don't know a better way of saying it. I think he's one of us. So it's really a fantastic thing that you've done here. And again, it's a wonderful pleasure to be here. So I'm going to be talking about really a line of work that one way or another I've been pursuing for the past 10, 11, 12 years or so. But this particular set of ideas have been the main focus of my thinking over the course of the pandemic. And it's reached some kind of, it's beginning to reach some kind of conclusions. So I want to tell you something about it. It's work done with a wonderful collection of physicists and mathematicians over all this time, but really specifically the work that I'll be talking about, the new work that I'll be talking about is work done in collaboration with the mathematicians Hugh Thomas and Pierre-Philippe Lamondin, and two wonderful young theoretical physicists, Giulio Salvatore and Hadley Frost. And we've already had some really great introduction about why amplitudes are so interesting and important. But the particular point of view that many of my friends and I have been exploring over this period of time is kind of a reverse point of view. So we know what amplitudes are. Well, you throw some particles in from infinity, they bang into each other, they go back out to infinity. If you're an experimentalist that's just sitting there at infinity, you don't know what happened on the inside. Okay? All you know is you've sent some things in, abracadabra, and some things came out. It's the theoretical physicist that comes along and tells you, here's what happened. Okay, what happened is the protons came in, and inside the protons there were gluons, and the gluons banged into each other, then this happened, and that happened. And you sum up all the ways that things could have taken place because of quantum mechanics. So we have these pictures, these Feynman diagrams that encode local interactions in space-time on the one hand, each picture, and then we sum over all the pictures, the sum over histories as Feynman taught us to be consistent with the principles of quantum mechanics on the other. So I want to emphasize that this is one way of filling in this black box of what happened. But no experimentalist is a little teeny tiny creature that's in there with the proton and seeing the gluons go in and bang into each other and come out. This is a picture that we put in to give a rational accounting for what actually happened. And we have lots of evidence, we've seen it in the past couple of talks, that this picture is perfectly correct. There's nothing wrong with it. It's perfectly correct, but it's hiding something. Being completely manifest at every moment with the principles of local space-time and quantum mechanics seems to make the answer look horrendously complicated, even though in the end it turns out to be incredibly simple and even have hidden symmetries. So when that happens, you start wondering that there might be a different way of thinking about what this problem is. In other words, what I'm talking about here is not necessarily better methods, more clever changes of variable, different cool ways of calculating the amplitude, which is of course wonderful and a very important part of this virtuous cycle that, that our previous two speakers were talking about. But in a sense, I'm not interested in getting the answer. At least in this philosophy, I'm interested in finding a new question. I would like to find a new question to which the amplitudes are the answer. And I would like to do that without putting in all the stuff on the inside that nobody actually sees. Nobody sees the particles whizzing into the intermediate of space-time and bang into each other going back out. Nobody sees the evolution of a state in the Hilbert space of quantum mechanics. All we see, at least if we're experimentalists at infinity, is the final result. And so what we'd like to do is put something else in that blob. And there's lots of other philosophical reasons you might want to do this. We have reasons to expect the notions of space-time are approximate. We even have reasons to expect that when it comes to very fundamental esoteric questions about applying quantum mechanics to cosmology, that quantum mechanics might eventually cry uncle. So there are reasons even to expect that we have to go beyond these principles of space-time and quantum mechanics. I'm not doing that. There's nothing speculative in this talk today. We're going to try to reconceptualize standard physics from a different point of view, where space-time and quantum mechanics are not primary, something else will be primary. And if we can understand what that something else is, it will also maybe explain where these magically, miraculously simple formulas come from, but perhaps ultimately give us a window into what deeper principles might give rise to space-time and quantum mechanics. And I want to emphasize this point because something that the theoretical physicists have been seeing a lot over the last 20 years is that quantum mechanics can be thought of as the apex predator, the king, and space and gravity can emerge from it in the sort of language of the gauge-gravity duality or it from qubit and all these wonderful developments connecting space and entanglement. But I think ultimately we're going to have to go an abstract step further than that. These all give us examples of emergent space, but not of emergent time. And the very deepest questions about the most existential questions of all involve the emergence of time as well as of space. My own feeling is that we're going to be looking for some even more primitive structures out of which we'll see quantum mechanics and space-time emerge together, somehow joined inexorably. And what we've been seeing in very concrete terms, this is not just sloganeering, it's really concrete terms over the past decade, are examples in a number of settings of exactly this phenomenon happening. And I'm going to show you such an example today. But before going forward, so let me say again, what are we trying to do? We're trying to find a question. Where does this question live? This question lives in the kinematical space that defines the scattering process. In other words, you give me maybe the momenta of the particles, that determines their energy. And that's it. You give me a list of n momenta. Perhaps you tell me what the spins of the particles are, if they're massless, what their helicities are. That's the data. Okay, the kinematic space is the space where the amplitude lives, and we want to find a question that lives there, whose answer gives us the amplitudes and all their richness and complexity. Okay, now this space seems like a very boring place. What could you possibly do in the space of n momenta of particles? That's the space that we're talking about. Okay, what kind of question could you ask in the space of n 3 momenta for particles? Well, that's what we've been seeing over the past 10 years, is the kind of questions that we have to ask there. And one of the striking things that we've been learning is that the questions have a remarkable combinatorial flavor to them. Okay? They involve ideas and actually interesting new ideas in mathematics, areas of mathematics that are just being recently developed by mathematicians, some of which we're running into simultaneously. And so that's why most of my collaborators over the past 5 years have been pure mathematicians, because we're running into the same structures roughly simultaneously. And sometimes physics is giving us generalizations of these structures that are surprising to the mathematicians. So what I'd like to do in the next few minutes is give you a first invitation to why the heck there is something combinatorial going on at all. There's something combinatorial. There are geometric structures. But when I say geometry, don't think of these cool, elegant universe pictures of Calabi-Yaos and these fancy, schmancy things. These are sort of very austere geometric structures. They're sort of like, they look like platonic solids or polytopes and higher dimensional generalizations of these kind of objects. They're geometric objects that are fundamentally determined by combinatorial ideas. Okay? And I think one of the most, one of the aspects that I personally enjoy the most is that ultimately the ideas can be explained to a bright student in high school, or as things are getting simpler even in junior high. So most of what I'm going to be telling you about today is sort of junior high school level mathematics. You just need to know how to add vectors. In the previous incarnation of these talks, you also needed to know how to take a determinant. We're not even going to need to do that today, mostly. We're just going to have to learn how to add vectors. Okay, but I want to give you a first invitation for why this is all true. Why this is all true, why there is something of this sort going on. And so just, we're going to take as an invitation the very simplest possible theory of just scalar particles, kind of like Higgs is. And the interaction they have is just this little basic cubic interaction. And so we're going to just draw all the Feynman diagrams that we can. It's just that here there's an ordering for the external particles. I'll explain a little more where the ordering comes from later, but the particles are labeled as you sort of go around a big circle at infinity, 1, 2, 3, 4, up to n. So for instance, if I'm just drawing diagrams at tree level, I would have the sum of these two diagrams. At 6 points, so 3 to 3 processes, I would have the sum of these diagrams and a bunch of cousins. Okay, and each diagram like this has some singularities, has some Feynman propagators that involve inverting 1 over p squared minus m squared, where p is some of the momenta that runs in this diagram. So for example, in this first diagram that have 1 over p1 plus p2 squared minus m squared. Okay, so, and in general, I can have a sum of consecutive momenta because of this sort of planarity. I just only have consecutive momenta, 1 over p squared minus m squared. I'm going to call that variable xij. Okay, so that goes just between I and j. I'm going to call it xij. And we're also going to use the following notation. Imagine that I draw the momenta end to end on a piece of paper. So P1, P2, P3, P4, and so on. By momentum conservation, you get a closed polygon. Okay? Momentum conservation is a statement that all the momenta add up to 0. And so there's a very natural thing that you could talk about is what is the distance squared between 2 points in this polygon? The edge lengths are P1, P2, P3, and so on. So the distance squared are precisely the propagators that occur in these diagrams. And you can see, and you can show very easily that that's actually a basis for all of the possible dot products that you can build. So this is going to be our kinematic space for this theory. Not the momenta of the particles directly, that's not Lorentz invariant, but we're going to take dot products of the momenta between the particles. Dot products is the actual kinematic space. And we're actually going to use these variables xij as another stand-in, a more convenient stand-in for all of those kinematic variables. All right, so now we have a more concrete version of our challenge. Here's our kinematic space. I draw this polygon. There's a variable xij associated with every chord on the polygon. That's my space. Go. Right? You have to find a question in that space whose answer is the sum of all the Feynman diagrams. Right? And so we'd like to see what could such a theory look like. Well, imagine we're some experimentalist that has their finger on the dial and is moving these momenta around. What are the clues that they might notice? What would strike them about this, amplitude that they're measuring, or cross-section? But I'm going to imagine they're measuring the amplitude directly. Well, the obvious thing they would notice, and any experimentalist would notice is the following, that if you move the momenta around, there are some places where the amplitude blows up. There's a resonance, the amplitude blows up. The poles are important. Now, how the experimentalist reacts at this point depends on what kind of experimentalists they are. And anyone who knows experimental particle physicists know they come in two types, those who really wanted to be theorists and those who hate theorists. Okay? So the hero of my story is going to be those who hate theorists. But the one who kind of wants to be a theorist says, oh, it's a pole. So I should see what happens to the residue near the pole, because I remember complex analysis residues are cool. So let's see what happens near the pole. And do very delicate, precise measurements around the pole, and they discover something remarkable, that the amplitude actually factorizes. It's blowing up like 1 over p squared minus m squared, but the residue is a product of two lower point amplitudes. Okay, so, and they go to their conference and they report this as this big clue as to what's going on. And depending, and there's some theorists in the audience, one of them is Feynman, and says, oh, I know what to do with that clue. This means that what's going on is that you have these processes in space-time. I add up all the ways they happen with Feynman diagrams that I just named after me. Okay, and another theorist in the audience that some of the physicists here may not have heard of, but every mathematician would have heard of, would be Pierre Deligne. And Pierre Deligne would look at this and say, no, I've seen this before too. This is the very first thing that you run into when you study the configuration of points on projective space. And if you take that configuration of points on projective space and you go to the boundary of that space, it exactly factorizes in precisely the same way. So these are the clues. And so Feynman says it's Feynman diagrams. Deligne says it has something to do with points on the boundary of a disk and what happens as you pinch them. And the first picture is a picture of particles in space-time. And the second picture ends up being related to the string worldsheet. Okay, so this making factorization the star of the show is related to the two ways that we've known of for 50 years, 60 years for describing particle scattering in terms of particles in space-time and in terms of strings. But the hero of my story is the lazy and smart experimentalist who doesn't want to do any detailed measurements. They're just excited by the fact that the amplitude blew up. So they're now going to move the dials around some more and try to make it blow up more. They're like a little kid, so they want to make it blow up more. Okay, so if they do it at 4 points, they'll be a little frustrated because if they design, let's say, P1 plus P2 squared equals m squared, that's still blowing up. They make everything else, they can't make it blow up anymore. Okay, they can also make P2 plus P3 squared equals m squared. Okay, but they can't make it blow up twice. But when they go to 5 points, they can. For instance, they can have P1 plus P2 squared goes to m squared, and they can make it blow up more, mathematically double pole, 2 poles, if they also then P1 plus P2 plus P3 squared goes to m squared. Okay, but they'll discover there's a pattern that they can make it when P1 plus P2 squared goes to m squared, but not when P2 plus P3 squared goes to m squared. Okay, so there's some interesting pattern of how the multiple blowings up can occur. And they want to go to their conference. So if I say this in the language of my little polygon that I was drawing, there are some patterns of poles. Remember, every pole corresponds to a chord on this polygon. There are some pattern of chords that are allowed and some that are not allowed. And the ones where the chords cross each other are not allowed. Those correspond to sort of processes where I have a pole and to the particle physics of the S channel, the T channel at the same time. I can't have that. There's no local picture in space-time that lets me see both those poles at the same moment. But I can have the chords not cross each other, and then I can have any number of them that I like. And I can go all the way to have so many chords that I fill up the entire polygon into a triangulation. And what does that correspond to? That corresponds to a single space-time process. Okay, that's a single Feynman diagram, the complete triangulation. Okay, so now we can say a little bit more. Remember, our kinematic space is just the space of chords on this polygon. I have variables xij associated with every chord. And now there's some patterns. There's some, whatever the structure is, has to do the following thing. It has to tell us that we're allowed to see poles when the chords don't cross, but crossing chords are not allowed. That's the physics of locality in space-time. Okay, so that's the fingerprint of locality in space-time on the answer. And furthermore, we have to have that if you go in the neighborhood of some xij goes to 0, well, the amplitude has to factorize into the product of two things. And what is it factoring into? Well, the obvious thing. You just cut the polygon in two, and it's the product of the amplitude that you get from each of the two polygons. So that's locality and unitarity are translated into these sort of simple things that have to emerge. All right, so now our experimentalist goes to their conference, and they actually realize that this pattern of poles has a shape to it. Okay, so they're trying to explain what the pattern looks like, and I'll tell you what it looks like already at 5 points. It's not maybe super impressive still here. It's completely coincidental that it looks like a pentagon, and we're at 5 points. So I'll show you a more interesting thing in a second. But you see, remember, they're excited about how many poles, how much they can make it blow up, how many poles there are. Well, this shape tells you that this side of the shape corresponds to having this chord go to 0. This one has this other chord go to 0, and this vertex is both of them going to 0. Okay, so what does this picture do? This picture is decorating this shape of the pentagon in a way where you can think of it as the interior as nothing blowing up. The first faces, in this case edges, are just one thing blowing up. The vertices is two things blowing up in a way that's compatible. So that means that I'm decorating this shape with partial triangulations of the polygon, which you can also think of as sort of partial factorizations of the amplitude. Right? So it's slightly non-trivial if you look at this picture that you can actually do it for the pentagon. It closes in on itself in a consistent way. For 4-point scattering, it's a little bit more trivial. The picture just looks like an interval, and the inside is a square, and on one side it's triangulated one way, the other side is triangulated the other way. But now, this is a little more interesting. If the experimentalist works really hard, and they do the 6-point scattering example, they'll see there are 9 ways that it could blow up once, 21 ways it could blow up twice, and 14 ways it can blow up 3 times. And if there's some sort of shape that you could draw with it, it would have to be a 3-dimensional shape. And they might sort of give up trying to see if they can build a 3-dimensional shape. Could there possibly be some kind of funny 3-dimensional shape that has 9 faces, 21 edges, and 14 vertices? Well, one piece of encouragement, if you remember from high school mathematics, is the number of vertices minus the number of edges plus the number of faces is equal to 2 when something looks like a ball. And so 9 minus 21 plus 14 is indeed equal to 2. So there's a chance that there's a nice shape associated with it, and there is. That's the shape. Okay? And I invite you to fill in the rest of the shape if you want to have some fun. This is an interesting shape. All the vertices have been decorated with complete triangulations of the hexagon. And I've just shown you what some of the faces look like. So this is a face which corresponds to this one chord. This is the face going to the other chord. This edge is 2 chords, and again, the vertices are 3 chords coming together. I didn't decorate the whole thing. It would look a little too busy. Okay, so this shape is known as the associahedron, and this is a non-obvious fact. That this is not in all the textbooks, that the sort of pattern of the poles, of how the poles together, are captured by a shape. Okay, but it's a remarkable fact. It's a sort of remarkable, very basic fact that does something about space-time and quantum mechanics that is not in all the books. And in fact, this fact knows the other fact. This fact knows what the closet theorist experimentalists noticed. It knows about factorization. The reason is that factorization is encoded here in the fact that if you go to a facet of this polytope, the facet of this associahedron actually looks like the product of lower associahedra. Okay? So we see that in this example, this has 6 facets that look like pentagons and 3 facets that look like squares. And the ones that look like pentagons are exactly correspond to these factorization channels with a 5-point amplitude on one side and a 3-point on the other. And the squares are a 4-point amplitude on one side and a 4-point on the other. Remember, the 4-point amplitude is an interval, and an interval cross an interval is a square. Okay, so the fact that the poles are captured by the shape is an interesting thing that we didn't know before, and it knows about the other stuff that we did know about before. Okay, so this is a clue. As I said, this is an invitation. The particle and string pictures don't know about this. Okay, at least they don't obviously know about it. It's not at the forefront of how we think. But this shape does know everything that the particle and string picture did know. Okay, at least at this very basic level that we're talking about. So we'd like to know, how can we make this obvious? Okay, so we'd like to find a way of thinking about all of this subject to make this kind of fact obvious. And whatever it is a qualitative clue to the kind of theory that we're looking for in kinematic space, the question that we're looking for in kinematic space. So now we want to ask a question about these stupid polygons with the chords, whose answer is that. Okay, we'd like to know what kind of question about the space of X chords on a polygon has this guy as its answer. Actually, back in 2017, with a number of friends, we ran into a very particular realization of this associahedron. If you look carefully at the sort of combinatorics, the pattern of how the facets meet is exactly the same as in the previous picture. But it's a very, very special particular shape. There's a bunch of parallel sides and so on. And this was something that was sort of just happened on by some guesses and lucky analogies from other parts of physics and other things that we'd seen earlier in the story of the empatahedron, which was, in a sense, a much fancier version of the kind of things that I'm talking about now. But it was artisanal. It wasn't conceptual, not entirely conceptual anyway. And we'd like, as much as possible, to not do things in an artisanal way. So we'd like to have a completely canonical, conceptual understanding for where these things come from. And again, this is a qualitative clue to the theory in kinematic space that we seek. All right, so that was the invitation. I have another 15 minutes, and I'm not going to cover the 2 years of very intense work over the course of the pandemic to tell you everything that we found. But I want to give you at least a flavor of what some of the ideas are and why, in this way of thinking, and at least tell you something about the content of the title of how particles discover strings. Okay, so let's now go all the way back to a basics. What's the theory that we're talking about? We're talking about the simplest cousin of the theory of gluons that Lance was telling us about in the previous talk. So it's a theory of just scalar fields, and the scalars are colored. So they're just colored, they have colors and anti-colors, just like gluons do, but they don't have any spin. And so this theory has all of the structure of the, if you like, the denominators, the singularities of the amplitudes, but none of the numerators, none of the exciting, interesting stuff in the numerators that make gluons and know about spin and the Yang-Mills structure and so on. All right, so so we would conventionally say that this is a scalar with an upstairs and a downstairs color index. There is a Lagrangian, and famously, going back to a 't Hooft, in the 1970s, we can think about the Feynman diagrams here in what physicists call a double line notation. Sometimes it's called fat graphs or ribbon graphs. Again, every line there represents a color and an anti-color. So the basic interaction is this cubic interaction, but I can glue them together to make, these are some examples of, these are the tree amplitudes that we saw for the, here are some one loop corrections. Here's a two loop correction that can't be drawn on the plane. So it would be called a non-planar two loop corrections and so on. All right. Now, in fact, right away, and a 't Hooft noticed this, and this has been a big part of the -1th order connection between particles and strings. Right away, just drawing Feynman diagrams gives you a two-dimensional surface. Okay, and it's just because the diagrams literally give you the triangulation of a surface. So if I go back, we saw this already before. So here is a disk with 5 points on it. I was drawing it before like a pentagon. Here's a triangulation, 1, 3, 1, 4. So I've triangulated this disk. And now here is the corresponding Feynman diagram. It's just literally the dual of that diagram. And if I now fatten all the lines of that diagram, I just get literally a triangulation of the disk. In fact, you can think of every cubic vertex as representing a triangle of the triangulation, and every propagator as a rule for how you join two edges of a triangulation together. If you were blind and you couldn't see a surface, if you wanted to teach a computer how to, like, record a surface, there's a nice computer program called Flipper that plays with surfaces and so on. Flipper can't see. You give Flipper a sequence of triangles and how they're glued, which is literally the same as giving it a single Feynman diagram. Okay, a single one of these ribbon graphs. So I want to emphasize one diagram here defines a triangulation of an orientable surface by giving a triangulation for it. Okay, and some other rules. So how do I read off from the surface? How do I read off the momenta of the particles? Well, we saw an example already, but I can say it a little bit more abstractly now. You imagine that all the boundary components are labeled by momenta, and you draw any curve on the surface you like, and you assign a momentum to that curve by the homology of the surface. That means that you take that curve and you deform it to any of the basis curves that you can. Okay, and so for instance, in the picture that we had before, the reason I assigned this x p1 plus p2 plus p3 squared is because this curve is homologous to that one. I can deform it to look like this one. Sometimes, here's an example that will correspond to a one loop diagram. Sometimes there's a curve on the surface like that one, L, whose momentum is not determined by the external guys, and so it's undetermined. That's what we would call undetermined loop momenta that we integrate over. If that's fine, you can make any basis choice for them that you like, and then all the other momenta for every other arc, every other curve is completely specified again by homology. All right, I'll skip over some of these details. All right, so what we've seen now is that just any one Feynman diagram defines a surface. So there's the beginning of the notion of a surface. But we can now ask our question again. So now we know how to define our kinematic space. Our kinematic space is, I choose any one diagram representative that gives me the surface. Now I have the surface. My kinematic variables are all the arcs on the surface and the momenta that go along with. Okay, so that's my space. This surface and the space of all the arcs on the surface. And so now we can again come to our question. And the most basic question is, why do we have space-time and quantum mechanics, right? And in this context, it means, why should we think about every possible triangulation of a surface? You know, one of them defines a surface. Why do we care about every possible triangulation of the surface? Every triangulation corresponds to some Feynman diagram. So we know the right answer is we're supposed to think about every triangulation of the surface at the same time, and we're supposed to add them all up coherently with all plus ones, right? So why should we do that? Why should we take all of them together? That's space-time. Why should we add them all coherently the same weight? That's quantum mechanics. All right, now what I'm going to tell you in the next 10 minutes, I think I'll at least be able to explain this much, is that the answer to this question is actually lying in plain sight. When we concretely think about labels, just really how to think about curves in kinematic space. And this is going to be the kind of conceptual origin of that associahedron and all the other things that I was telling you about before, although I won't get to talk about the direct connection, but I'll tell you something specific and true in the next 10 minutes. This picture does give us a new, of course, much more efficient ways of computing amplitudes. And I emphasize the amplitudes here, partially because most of the work in this particular substream of the subject in the past 10 years has been about what you get before you do the loop integrals, before you get the actual amplitudes. Doing the actual loop integrals gives you these fascinating transcendental functions that Lance was talking about. And in the connections that we had with combinatorics and geometry, we were leaving that part to later. We weren't doing that. Well, that's no longer true. We're talking about full amplitudes now. And there's going to be no reference to the diagrams at all. And it's going to expose some hidden symmetries. At the same time, this picture, which is fundamentally about particles with the two-dimensional surfaces, just about the combinatorics of Feynman diagrams, hands us really on a platter the generalization from particles to strings. This is not one of those things where we say, oh, imagine you have little point-like particles. Gee, I wonder what would happen if there are little loops of string instead. There's something in the structure of particles that tells you to think about strings directly. Okay, and that's I'm probably not going to get to that in the next 7 minutes, but I'll give you a sense for it. Okay, and in fact, it gives us new representations of string theory amplitudes, with no reference to the worldsheet of string theory or the cognoscenti that we'll know about worldsheet conformal field theories, vertex operators, all of that stuff. None of that is here. Instead, we're going to have a completely combinatorial definition and description of what these amplitudes actually are. All right, and there's sort of three parts to this story, and I'll only get to tell you about the first one probably in the time I have left. But we're going to see pictures like that little funny 5-point flag on the left. And we're going to see that pictures like this are going to tell us at the most zeroth order about how space-time processes exist and have to come together and fit all together, and you have to consider all of them together. The answer to this why space-time and quantum mechanics question is sitting there in a very simple way, just thinking about labeling the curves on the surface. Associated with that fan is the generalization of that polytopal shape that I told you about. So I told you about this associahedron that we saw already at tree level. There's something like that associahedron at all loop orders. It has nothing to do with associated with any surface. And finally, there's a direct relationship between both of these things and the following fascinating set of nonlinear equations. For any surface, you associate a variable u of x with every curve x on the surface, and you plot down the following equation. U sub x plus the product over all the other curves, u sub y, to the power of the number of times the curves x and y intersect each other, equals 1. Okay? This extremely simple equation turns out to be the kind of origin of much of the magic. There's ways of solving these equations. You can try to solve them directly, and actually we're learning to solve them directly. But one way of solving them brings to life ideas from hyperbolic geometry and begins to look like some ways of talking about the string worldsheet. But it's not the most fundamental way of solving these equations. The most fundamental way of solving them introduces certain kinds of polynomials and certain counting problems that are fundamentally associated with category theory. And I know this might sound completely insane. It certainly would have sounded insane to me. I was definitely one of the dyed-in-the-wool theorists who would think that the last thing in the world I would ever care about is category theory. It just sounded like abstract nonsense. But this is really a case where it has absolute teeth. Absolute beef and teeth, and tells us how to do things that we don't know how to do otherwise. But I'll just try to give you an idea about the first part, and then end. So what are we going to do? We're going to think about labeling curves on the surface. And so remember, a surface is just handed to us by one of these double line notation graphs, fact graphs, ribbon graphs. And we're going to think about a curve on the surface as just taking a walk on the graph. Okay. In fact, what we're doing here, if you think about taking a walk on a graph, remember, before I was drawing a curve like 1, 3, this is something that you might call a chord. We're going to do something slightly different here. Remember, these surfaces are all orientable. So I'm going to push the endpoints on the curve a little bit according to the orientation of the surface. Okay, so instead of going from 1, 3, I'm going to push the endpoint so it goes from a little bit to the right of 3 to a little bit to the right of 1 to a little bit to the right of 3. These things are called laminations and not chords. But the laminations are actually the most obvious things by imagining taking a walk on this graph, right? After all, if someone told you this is your road, take a walk. Well, I could start on the road 2, 3, and then I'm going to make a left onto the road 1, 3. And then I'm going to make a right onto the road 1, 4, and then I'm going to make another right onto the road 5, 1. Okay? So how are we going to label a curve on the surface? Nothing other than this Google Maps directory, okay, of how to navigate. Where do you start? And you go left, right, left, right, left, right, and that's it. So every curve is associated with a word like that. Okay, and I'm just denoting going. Left by up and right by down in these curves. Okay, so I've drawn what every single curve looks like. Now, another natural thing that you could do, and that's it. That's our fundamental building block. Okay, we're just thinking about the curves as these words. But another natural thing you could do is just record an integer vector for which one of the roads you hit. Okay, so for instance, this 2, 3. This laminate that we just drew would have a non-zero values in the locations 2, 3, 1, 3, 1, 4, 5, 1, and 0 everywhere else. Okay, so that's called a geometric vector for obvious reasons. What is this space that we're talking about? It's a 7-dimensional space in this example, right? I have 5 boundary guys and 2 internal guys, 1, 3, and 1, 4. So every curve, there are 10 curves, and every curve has some 7-dimensional vector that just records who you hit along the way. Okay? So those are called geometric vectors. So I have 10 of them in this example. It's a 7-dimensional space, so I can choose a basis of 7 of them. It's very natural to choose the basis to be the boundary guys on the outside and the 2 internal ones that were there in the triangulation to begin with. So that's my basis. And so I can write the remaining 3 vectors as a linear combination of those 7. Right, so that's just an exercise. This is what you get. Okay, So that's L24, L25, L35, and I'm just writing them as linear combinations of the internal guys that are 1, 4, and 1, 3, and the external ones that are 1, 2, 2, 3, 3, 4, and so on. Okay. So far, nothing interesting is happening. Okay. I just have a bunch of vectors. They all have integer coefficients. They're all positive. If I looked at them in the 7-dimensional space, it just all looked like some cone going out in some direction. Nothing interesting is happening. Now, the first slightly magical thing happens is we're going to look at this picture in a particular direction. We're going to stare at it in the direction of the external boundary laminates, 1, 2, 2, 3, 3, 4, 4, 5, 5, 1. In other words, we're going to project through those directions. That's the motivation for it. That's like saying the guys on the outside are different than the guys on the inside. The guys on the outside are frozen. They're on shell. They're just locked to the masses of the internal particles. So we want to sort of go on shell by projecting through them. And projecting through them just means that I now have a 2-dimensional picture. I started with a 7-dimensional picture. I'm going to project through 5. So I have a 2-dimensional picture. But in this 2-dimensional picture now, I can write all of the vectors as a linear combination of 2. Let me choose them to be G13 and G14. And so you can see, what do I get for G24, G25, and G35? Well, all I have to do is ignore the guys in red, because I just projected through them. Okay, so here, so far so good. There's a nice formula here we can work out. There's G24, there's G25, there's G35. And there turns out to be an extremely simple rule for reading off this final answer without going through this whole process directly from the word. You just look at the word, and in every peak, you put a plus sign, and every value you put a minus sign. And that gives you the geometric vector. So for example, for 1, 3, and 1, 4, we get plus 1, 3 and plus 1, 4 because, oh, sorry, I should have done it the other way around. So it's plus values minus peaks, and so on for the rest. All right, so now what has that done for us? Now we have an interesting picture, but now let's plot what these vectors look like. And now something remarkable happens. This example is still a little small, so you might not be super impressed, but you'll get the idea of what is going on. So remember, here is 1, 3, 1, 4. 2, 4 was minus 1, 4 plus 1, 3. 2, 5 was minus 1, 3. 3, 5 was minus 1, 4. So I've just plopped down those 5 vectors that I got after projection. And now look what happened. These vectors are now dividing the space, they're tiling the space into pieces, into little cones, right? And furthermore, who are the cones? See, it's really cool. This cone is bounded by the vectors 1, 3, and 1, 4. Well, 1, 3, and 1, 4 are exactly 2 compatible chords that give me a triangulation of the polygon. So this little region is actually associated with this triangulation of the polygon, which is this Feynman diagram. This region is another triangulation of the polygon, another Feynman diagram. And so what we've done, purely doing nothing other than looking at the labels of the curves and going on shell by projection, we get a picture where we have a space that's tiled, completely tiled by cones, and each cone is a Feynman diagram. Okay, so that's the sort of the most 0th, even -1 order emergence of space-time processes on the one hand. Those are the cones that do the tiling. And the fact that you have to put them all together and not leave any out, because only all taken all together and treated democratically do they tile the entire space. Okay. Now, there's various general things to say about the existence of this fan. I don't have time to explain it. The existence of the fan, though, the one thing I will say is that normally when you think about diagrams, you think about here's a diagram, here's another diagram, here's another diagram, kind of like what Lance was saying. Somehow when you have a huge number of diagrams, you want to sort of think about them all melded together and not sort of individually. This picture is a sort of step in that direction because it tells you they're not all totally independent things. Some diagrams are next to others, they touch others. So they have to be taken together and they tile the entire space. That fact that you can take them all to tile the entire space is associated with a certain hidden symmetry, even of this stupid scalar theory that you might not have thought had any hidden symmetries. And to the cognoscenti, they'll say this hidden symmetry is a real sharp analog of the dual conformal symmetry of n equals 4 super Yang nulls in this setup. Except here it has nothing to do with planarity. But final thing that I'll mention before ending, I know we all are eager for the reception, but I can't resist talking about this here at UCLA, is the fact that we have a complete fan gives us an opportunity to do something that I think Schwinger would have very much liked. It gives us a unified form of Schwinger's parameterization of Feynman diagrams. What I mean is the following. So let's say we just take this one region by itself. If I take this one region by itself, Schwinger tells us to think about the propagator as an integral, 1 over p squared is an integral of 0 to infinity e to the minus alpha p squared d alpha. That alpha is called the Schwinger parameter. So we can think about, for example, the value associated with this diagram in this little region here as just being associated with an integral over 2 Schwinger parameters associated with 1, 3, and 1, 4. And if we didn't know anything about the span, someone could tell you, well, do that for every single diagram, add them all up. It's super lame. I mean, they're all just 2-dimensional integrals, but you're just artificially adding them all up together. Well, when there's a fan, there's more of a reason to hope that something good will happen because they naturally are glued together in this way. And in fact, there's a very pretty formula. If you could come up with a function, u sub x, that has the property that u sub x evaluated, it's like a Green's function. U sub x evaluated on the ray y is equal to 0 unless x equals y. If you had such a function, and this function can't just, it has to be sort of piecewise linear. So it has some linear function in this cone, some other linear function in this cone, some other linear function in this cone. So it has to be an interesting piecewise linear function. Then if you could do that, then you can write down, you can think about all the Schwinger parameters at the same time for this one graph, except in every cone, only some of the Schwinger parameters turn on, the other ones are 0. When I go to another cone, a different set of Schwinger parameters turn on, the other ones are 0. And in that way, when you integrate over the entire space, you actually get the sum of the entire amplitude. Okay, so if you could find such a remarkable function which does this, then that could work. And that gives you, if you could do that, since this fan exists for any surface, you can attempt to, you can imagine that such a function exists for any surface, and you can write down formally a formula for the amplitude now associated with any surface, including at loop level, because again, one of the points of Schwinger parameterization is that it trivializes doing the loop integration, turns them into Gaussian integrals. And so what you get is a formula for the final amplitude that looks a lot like formulas that people, the cognoscenti, will recognize as involving Szymanczyk U and F polynomials, except these are just small generalizations of U and F polynomials, not associated with the graph, but just associated with the surface. But really, for any surface, you have all the arcs on the surface. There's Schwinger parameters associated with every arc on the surface, and there's a polynomial in those guys. And this is a formula that is really a concrete formula that would sum all the diagrams together into a single object. Okay, and just have a single big Schwinger parameter integral that does everything. But very naively, finding this function that lights up one ray is just as hard as enumerating all the Feynman diagrams. See, what is it that we want to do? Essentially, we're trying to ask, let's say you hand me a random vector in this big fan. I'm trying to figure out which cone am I in? Well, very naively, which cone I'm in, I've got to first enumerate all the cones and then check, am I in this one, am I in this one, am I in this one? Oh, finally I'm in this one, okay? So that's basically tantamount to like enumerating all the Feynman diagrams. Okay, so this looks like, you know, we've somehow unified everything together, but we haven't bought anything over the picture of Feynman diagrams. And in fact, you could try to do this for any old fan. You could try to invent something that you could call amplitudes associated with a random fan like this, a random collection of cones. And you could write down this formula, everything would be fine, and it would be useless. Okay? But our fan is very, very special. And it has a second magical feature. So there are 3 magical features here. This is the second magical feature, which is that this fan is made out of very simple pieces. And I'll illustrate how it works again in this very simple example. So this already looks pretty simple, but it has sort of 5 cones. But in fact, I can generate this thing with 5 cones by drawing on top of each other just 3 simple pictures. So I take this simple picture, and that simple picture. And if I sort of draw them on top of each other, mathematically, this is said to be the common refinement of these fans. If I draw them on top of each other, I can generate the more complicated fan. Now, each one of these pictures is very naturally associated with a certain function. Let's look at this picture. This picture is naturally associated with a function, which is the maximum value of 0 and minus T2. Why do I say that? Because what is the maximum value of 0 and minus T2? Well, up here, it's 0, and down here, it's minus T2. So there's this function has domains where it's linear, where one term dominates over the other, and that just produces exactly such a fan. Okay, so there's that one, there's this one. This one's slightly more interesting. It's a maximum value of 0, minus T2, and minus T2, minus T1. But now, given this set of objects, you can now say, can I build a linear combination of them that has the property that I want, that it lights up one ray at a time? And you can. Okay? And here they are. Okay? There's this particular linear combination. So U13 just lights up the ray 13. U25 just lights up the ray 25. But what I want you to notice is very mild in this example, but it's the start of the road, is that there's 3 functions, and they're producing 5 cones. So I did not have to enumerate every diagram by itself in order to figure out how to generate all of them. Of course, this gets much more exciting at larger n. Okay, so for instance, that's what the formula is. Very remarkably, at tree level, the only functions you ever encounter are these things, Fij, that are just that interesting a generalization of what we saw before, that interesting set of maxes. And that's the formula for all the u's. And the remarkable thing is the number of these f's is of order n squared at large n, where n is the number of particles. But how many cones are there? That's the famous exponential growth in the number of Feynman diagrams. There's 4 to the n cones. Okay, so I didn't need to do 4 to the n amount of work in order to generate everyone. I can produce this very complicated fan by just drawing on top of each other n squared, little, very simple pieces. This is a hidden simplicity and the hidden symmetry. If you took that fan and you just moved the vectors around a little bit, you wouldn't change any of the sort of most of the qualitative things that I told you about, and this would completely be smashed. Okay? This is crucial to this fan that comes from the picture of the words and the peaks and valleys and all of that. Okay? So that's all we've done so far. Just the words, the peaks and valleys, projection, cones, this observation that what we get is putting on top of each other incredibly simple pieces. And this is actually associated with actual formulas. Okay, so I told you that if you could do this, you could find these unified Schwinger parameterizations for loop amplitudes. And so I'm not expecting you to absorb these in any detail, but this is all the tree amplitudes and all the one loop amplitudes in this theory in any number of dimensions. And they're just concretely integrals. There's some integral over an n-4 unit sphere, n1 unit sphere at tree level and at one loop. And these are not formal integrals. You can put them on the computer. We've done it. You want the 20-point one loop amplitude? Press return. You just get it numerically. You can just Monte Carlo these integrals if you like. Okay? But you'll notice they have inside them exactly these building blocks, which are sort of magically producing this exponential complexity in the cones, all the diagrams from a small number of only polynomial building parts. All right. How is this related to that picture of the associahedron? This picture of the fan is in a precise sense dual to that one. If I go back to the associahedron, if I take this picture, if I take the normals to the facets of the associahedron, give me exactly the rays of this fan. If I take the normals of the facets that encircle a vertex, that gives me one of the cones of this fan. So the normal to the facets are rays of this fan, and the vertices of the associahedron are cones. So again, in a precise sense, the polytopes are dual to the fan. All right, I think that's all I will have time for. So I won't be able to tell you about how this is all related to strings, but maybe I'll just flash this formula and then just to give you a flavor of what's going on. So remember, we just saw that we can build these fans out of these simple pieces that are associated with these very simple functions like max of 0, minus T2, minus T2, minus T1. And if you stare at these a little bit, and if you've heard anything about tropical geometry, you would immediately associate this function with an interesting polynomial. You'd associate with that function, little f2, a polynomial, capital F2, which is 1 plus y2 plus y2 y1. Now, why do I do that? Imagine you put that y is equal to e to the minus t. So y1 equals e to the minus t1, y2 equals e to the minus t2. And let's just see what happens as I go off to infinity in the t-plane. As I go off to infinity in the t-plane, various of these monomials in F might dominate. 1 might dominate, y2 might dominate, y1, y2 might dominate. And who dominates depends on where you go off to infinity in a piecewise linear way. In fact, as you go off to infinity, the polynomial f2 becomes the exponential of that little function f2, which is the max of 0, minus t2, minus t2, minus t1. Okay, so if you make this move, where you go from this piecewise linear function now to this nonlinear function, okay, but this nonlinear function whose behavior at infinity is capturing the piecewise linear behavior, then you can take those formulas that we had for the U's before and now find what their nonlinear avatars are. That's what their nonlinear avatars are. One of the interesting things about them is that when these little variables y are positive, these variables are between 0 and 1. But clearly, as we go off to infinity in this t-plane, these u variables just reduce to what the variables we were just talking about a moment ago that gave us this unified form of the Schwinger parameterization. So it's natural to ask what happens if we use these nonlinear variables instead of these piecewise linear ones. And the answer is, instead of getting particle amplitudes, we get string amplitudes. Okay? So, so the path from particles to strings is, if you like, de-tropicalizing, recognizing these piecewise linear expressions that were sitting there in the structure of particles. See, I didn't say anything about strings until now. We didn't need them. They're not there. Okay? This fact about the fan, this fact that all these things are just the combinatorial fact about the words that label curves associated with Feynman diagrams. Okay? But that structure, the magic is that that structure is built out of simple pieces, drawing these guys on top of each other. It's that fact that they're writable as a small number of simple pieces, a common refinement of a small number of pieces, and that those pieces are these simple tropical functions that begs you to look at the nonlinear version of them. And the nonlinear version of them turns particle amplitudes into string amplitudes. Okay, so that's all I'll say about it, other than say that it actually works at tree level at one loop. I mean, anything you do in a string theory textbook that's calculated in a string theory textbook, you can calculate in this way as well. But there are some interesting questions about where you get something a little more general than ordinary strings. There's no restriction necessarily on d equals 26 on the space-time dimension, on the spectrum, and so on. There's a class of sort of stringy objects, and something extra special happens at the points where that string theory chooses. But there's something very nice away from those points as well. And in any case, the connection to particles has nothing to do with that. So there's nothing to do with the 26 dimensions or any of the rest of it. The final thing I'll say quickly is that the connection the connection to strings goes via discovering these interesting nonlinear functions. And the fascinating thing is that these nonlinear functions satisfy those equations that I flashed up very early on in the talk, that if I take the u plus the product over all the chords that cross u to certain powers that's equal to 1, you can, that's the origin of the connection to a strings. You can show that these very non-trivial, these equations have consistent solutions. And there's one way of solving them in terms of hyperbolic geometry that manifests, to some extent, the connection to the world sheet. But that's actually not the way that we ran into them. We ran into them in this way, thinking about them as these interesting ratios of polynomials. And in fact, the connection with the hyperbolic geometry does not make it obvious that they're related to these interesting polynomials. So we want to, if we want to see how they're related to these interesting polynomials, we have to see something sort of underneath the seemingly two-dimensional stringy world sheet picture. And there is indeed a more elementary and fundamental underlying combinatorial structure that's directly associated with the words. And you go back to the word and associate the word as a certain generating function. So you really draw the word, you ignore the boundary segments, you draw the word, and then you look at it, what I call the relationships with baggage generating function, which is that you get to pick any variable in this word, but if you pick it, you have to pick everyone in its past light cone, okay, as you go up and down. So that's it. So that's a certain interesting counting problem, and that counting problem directly gives us these F polynomials. So the ultimate path from the kinematic space to the amplitude is we start with our surface. We think about any curve on the surface as a word. We can think about the peaks and valleys to give us this G vector fan on the one hand. We can build these F polynomials from the counting problem on the other. Having done that, there's this very simple path between the F variables and these U variables. And finally, these U variables are giving us this unified Schwinger parametric form. You can take the sort of directly the field theory limit, the tropical limit, and literally get representations of field theory amplitudes for any surface, or you can leave it. You can leave it in its maximal glory, and in its maximal glory, it gives us string amplitudes. All right, so I'm done. So I think over the past decade, we've been seeing concrete examples where the rules of locality and unitarity of space-time and quantum mechanics are emerging from more elementary mathematical rubric. That the common theme of the earlier story of amplituhedra and these surfacehedra are notions of positivity, topology, and combinatorics in kinematic space, which somehow manages to breathe physics life into seemingly austere and empty territory. And of course, it's interesting that these theories now, there's nothing to do with supersymmetry, nothing even to do with 4 dimensions, certainly has nothing to do with the planar limit. Okay, this is just very, very generic physics. And my own expectation is that we're going to see more and more magic as we get closer and closer to describing all aspects of the real world in this way of thinking. Thank you very much. Oh boy, sorry about that. We can question while drinking.
Maybe everyone wants to get to the reception, so let's thank Nima again for his awesome talk.
Sorry about that.
Yeah, so alcohol outside, food inside. Also, the lectures tomorrow. So that'll be the beginning of Schwinger Fest, and 2 talks will be part of ManiFest. And that will not be here. It's Physics and Astronomy building, 1st floor. Okay, don't come here, go there. Okay, enjoy. What is this thing? I don't know what that is.